can apply, I was just saying I could give you this in your test, but I didn't, but we could apply our same principles of induction to whatever thing that I'm saying, can you prove this? And you don't really need to know too much, I don't think. Well, maybe some of the properties, but here we go. So are we happy to do the first bit? Go, you good things. Absolutely, you do your PN. So who did that in the test? They just wrote PN up the top. Fair enough, right? So there's our PN and N. So I'm going to be as lazy as Jack. Done. P1. So left-hand side, what's your first term there? This is when you sort of go, it's too easy. It's too easy to be true. And your right-hand side is also Z1. So that equals our left-hand side. Therefore, P1 true. Okay, what are we going to do now? Assume PK, that's right. So yeah, nothing new there. And we want to prove. So the only thing that's bugged us so far is that our wrist might be hurting because we're just writing a lot. Oh, Mr. shakes his wrist at the time. Okay, so what are we proving? We're trying to prove that Z1 times Z2. Dun, 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 dun. What was the tip again? Always include your kth term. We should have a race in writing. Dot, dot, dot. So same sort of thing. We've got Z1 times Z2. Like I'm looking at this and going, again, Dylan, I was listening to some of the sounds coming from outside, so I didn't exactly hear what you said. But using PK, can you see that this goes, it's just saying all of this, we can separate it to be. So one of the things I was thinking of is, could I look at this left-hand side and then just times it by ZK plus 1? And then using PK, you can turn, but we can say from here, we can actually say Z1 times Z2 times ZK, that is ZK plus 1. Do we agree? Why can we say that? Well, this one is a rule, is it not? Yeah. Right, so this is using, am I trying to prove that rule? No, I'm not trying to prove, so the thing was, aren't we trying to prove that rule? We're trying to prove the rule that it works for multiple, Z1 times Z2 times Z3 times Z4, right? But what we're saying here is I can use, oops, this one where I've just got 2. Right, so I've just got, oh, I did it again. I've just got 2 things there using that rule. I'm okay there. And then the next step is, what do we know about all of this? That is our PK, that's right. So this is going to be then Z1 times Z2 times all the way up to ZK, and then we've got ZK plus 1. Oh, it's one of those. Oh, am I allowed to do that? It seems too simple. Yes, we can. Obama. Using triage. Yay, and we're done. Hence prove that the modulus of z to the n equals the modulus of z to the n. Why? Why can I now go, yeah, baby? Hence. Anybody? How can we use this thing up here to help us prove this? I'll pause it while you think. So if, as Sky said, if like Z1 is Z, Z2 is Z, etc., right? Using this statement, we are saying then that Z times Z times Z, right, all the way up to Z n times. And so that will equal Z times Z times Z, again, n times. Correct? And just from the definition of what to the power of n is, then that has to be Z to the n. But make sure, again, it's hence, so make it clear how you're using part A. Ask, right, for part C, how are we going to use the thing above? And I said, how many of you are out there going, yeah, don't know what to do? And I'm looking at you, and the people who don't know what to do, you haven't got your pen in your hand. You've got your pen in your hand, but you haven't touched anything to paper. So if we're looking at this, what I should expect you to do is write down, okay, Z cubed, Z to the 30th equals, and again, look at that hence. What did you just prove? This thing here. So again, you don't know what's going on, but do you agree from the thing above that it means this? Would you agree? Now, you haven't done a lot of thinking here, have you? All you've done is you've applied, and now I'm wanting you to go, well, what does this mean? The modulus of Z. When they've told you this is your Z here. What's that saying? Yes, so then let's just do it. I'm running out of room here, but down the side, you can actually work out what the modulus of Z is. That's 3/4 squared plus minus 1 squared, which is 1 squared, all rooted. Snag that in your calculator. Yeah? And then this answer you just take to the power of 30. Does that make sense? But can I ask, those people who, thank you for your honesty, said, I didn't know what to do, once you've written this down, did that sort of help you? So that's another lesson in, don't keep it all in your head. Put pen to paper, please. This is a great lead-in to some of the work that we're going to do in the second half of this lesson, is that you're going to be asked to find the powers of large complex numbers. Now, back in the day when we had scientific calculators and even the early graphic calculators, if you'd put in 3/4 take I to the power of 30, I mean, try it now. I don't know. I'm sure your calculators now could possibly do it. But it used to be that it would hit a mark and go, no, can't do it. Even to the power of 80 or 100, we're going to look at a thing called de Moivre's theorem later this lesson, and it'll help you find things like that a lot easier. Does it do it on the calculator? Anyone try? It doesn't. So this is probably the last two models of calculators it can work it out, whereas the ones before that, it wouldn't. Maths is changing. So just using those properties. So C we can separate to be. And then what is the modulus of 2 take 1? I. Yep. So you're doing the 2 squared is 4 plus minus 1 squared is 1. So this becomes 2 root 5. Yeah. Agreed? We're good? So I've done the hard work. You want to finish off with D, E, F? Yeah, I didn't record that because it was, I don't know, think it was straightforward. Just make sure that you're showing your working, your steps there, okay? The next bit, so don't worry about 9, you'll just be there all day, every day. But we now want to solve things like this example number 4. And this is where I think the book has been not so overly thingy. This first one here, right, that rule, that was in one of our modulus properties right at the beginning. And this one, they didn't really make that incredibly clear, but this is true. So if you add two complex numbers together, and we can prove this with vectors. Maybe they did that with one of the vectors ones, and we tend to skip it. But this is one. So Sky is laughing all the way to the bank. So it's Karen with your notes. So this is one to definitely add to your properties. Okay, so have you already written down these properties? I'd like to think you have, and then just make sure that you add that one to it. You've added, I think we're quite, hopefully, reasonable to see how this has gone. We want to get rid of the modulus because we want to work around. And last time when we were doing, what were we doing? The function stuff. We were graphing, we could remove the modulus by considering the positive and the negative and whatever. It's just, you can't do it with this, right? So we want to get rid of that modulus. And we square both sides. Why? Because we know we've got this property here that we're going to use. So now, once we've got our squared modulus, we go down and we say, well, that's what's inside the modulus times its conjugate. All right? Making sure that we have squared that 3. We can follow? Right? Now we have to use our third, this other property where we can, if we've got something to the conjugate, it's all inside. And the conjugate of 1 is just 1. So you're just taking the conjugate of the actual complex number that's in there. What have they done going to the next step? Expand the suckers. Yep. And then a whole lot of things cancel. So we've got 9z on both sides, 9 times the conjugate of z on both sides, they cancel. How many z times the conjugates? Get that on one side, and we can then get rid of the times 8, divide by 8. It's the same thing. All that's going to change is the numbers. Will you ever have the situation where your 9z's or the z's and the conjugate z's don't cancel out for these questions? No. Okay? So give yourself a little bit of a momentito and see if you can apply. Question 10a is basically we're just following through. But it's these properties that you just want to highlight because that's what you're going to use. Forwards and then backwards. Did you want me to do 10a with you or not? No. I have expanded. So hello, I forgot if I had recorded, but we just went through the example. So sorry if I did record already and you're hearing this twice. Did I record? I think I might have. Anyway, we're following this example very soothingly. So, squared to eventually remove the modulus, and you need to make sure that we square the 2 as well because you're doing this whole thing. We're then using this property because that's the one that lets us remove the modulus so we can play around with the z and get to it. And then to go from this step to this step, we are using the fact that if I have w plus, oops, not the modulus thereof, but if I have w plus z conjugate, then that is the conjugate of each one added together. And if you don't believe that, look at either algebraically, some complex numbers, or graphically. But this is one that we need to make sure that we've put in our notes. Okay, so we're carrying on, just expanding now the brackets normally. So we get 16z plus 16z conjugate. I really wished that I had left a line now because it's looking a little bit squeezy. So maybe I'll do that now. So we've got 4. Okay, plus 16z plus 16. What's 4 times 16 or 64? Oh well, too late, I've written. Okay, very nice. Okay, and now we can see that we've got a 16z, the conjugate of that. And now we can just gather our like terms, okay? We also know that z times the conjugate of z is the modulus squared. So we're going to go backwards. So using that one backwards, we get that squared. and I'll take away that 1 from the other side. No, let's be nice. Let's be very neat with our working and not make a mushed up. So plus 64 equals okay, now you can gather your like terms. So 4 modulus of z squared minus modulus of z squared is 3 modulus of z squared. And that's going to equal 16 squared minus 64. Okay, we're going to get rid of this times 3. So we will divide by 3. Okay, so I just asked my class what 16 squared takes 64 divided by 3, and I got 8. I said no. And I was suspicious that it wasn't 8 because I now want to take the square root. And yes, sometimes you will take the square root and it might be a yucky answer, but in this case I knew that it wasn't. Yeah, so now we can therefore say that the modulus of z is 8. If you're looking ahead at question 11, so can you just look at your question 11? Because now we can say we don't have to do 11, because would you agree it's pretty much the same as 10a? But what's 11b asking you to do? Sketch it. Now, from yesterday and your beautiful sketches that you did, do you remember what the sketch of this looks like? It's the circle, that's right. So if we have, oops, gone. Oh, I think I should have drawn the circle first because this might not be nice and symmetrical. I can draw a shape, that's cheating. That's pretty good, come on. Oh. They mock me, they mock me. They mock me. No, so Tom just asked me, do I have to draw it? And what he was not listening to, because he was so intently working, was that we have now said part B was saying on an Argand plane, sketch the complex numbers which satisfy. So that, I could ask you to just do 10A and go, but if I also said 11B, I could just give that to you. This is what it implies, that you have to do the algebra and then sketch it. So you don't have to sketch the rest for B, C and D, but now you also don't have to do question 11. So feel free to do 10D. What's the deal with 10D? Yes, Guy, yeah? Do the thing. Yep, so you're using the rule where you're splitting the modulus up, absolutely. So, excellent. Yep, so you can use that rule times the other side and then it becomes just like A and B and away you go. Okay, so can you please reinforce that? I know you know how to do it, but doing it a couple of times just cements it in your mind. It's a little bit, as we said, mindfulness. Nice, nice. And then do the next. So don't do 11, have a look at 12, which I quite like. He can do 11. Now, question 12. We're quite happy to do all of that. And again, take notice of how the diagram fits with the questions, because it's going to lead into then, they're not going to give you the diagram and you might draw that to help you understand where it's going, okay? So these are introductory questions where you do, here's part A, here's part B, here's part C, here's part D. A good test question might just be part D. They don't give you all the rest and you have to realise that's what you have to do, all right? Having said that, if you can't get part A, B, C, you're screwed. So sometimes it's a show that. Anyway, we're all happy to find the length of each one of these, but yes, our understanding of our cosine rule, it's been a while since we've done it. So our cosine rule is this one, and keeping in mind that it's connected with this A is opposite, that length is opposite that angle A. So when we go to do our cosine rule, we have been asked to find this angle here, so we have to start with this opposite length, so that's the deal. You can find from your Year 11 textbook that they give you this already rearranged and you can just sub it in. I can't stand that. I just sub in and then I rearrange because I'm a fan of algebra, as she says, and watch her stuff it up. But anyway, minus 2 times root 10 times root 41, right? Cos theta. So to get cos theta by itself, I first have to get rid of all of this paraphernalia. So it's going to be root 13 squared is 13, take 10, take 41, and then it's being times by all of this, so I have to divide by negative 2 times 10 times 41. That gives me cos... That gives me, it does still have the square roots. That gives me cos theta, but I've got natta behind me. That gives me cos theta. How do I get rid of the cos? Reverse cos. Inverse cos. So we get our theta, okay? So find the Cartesian equations for the locus of these points. Now, our book doesn't give us an awful lot of info, and it sort of does a little bit at the start of that chapter with the circle stuff, and then disappears. So on OneNote, I don't know why that's so small now, but anyway, on OneNote, under the regions, loci, and ignore the triangle inequality for now, but we're just going to give you, there's some examples there of what we're talking about. So if it says, you know, we're just looking at the imaginary part, that could be imaginary of z equals 2, that's where we've got a nice horizontal straight line, because our imaginary is basically our y-axis. Imagine if we had y equals 2, same deal. That makes sense? Okay, same with the real part. I do need to make this bigger because that's annoying me. Can I make it bigger? There we go. Same with down here, oops, right, if we've got the real is greater than something, well, then we shade in the whole section, and it's greater than equal to, so it's a solid line. If it was greater than, it's a dotted line. And you don't have to be writing this down because it's all on your OneNote. You have access to it. Okay, this is the one we've already covered. Agreed? Okay, please note it represents the circle, center 0, 0, and so on. Don't worry about that one just yet. We'll come back to that. Uh-oh. There should be, I was going to say, there should be another one. We will have a little bit of an opportunity soon to have a bit of a worksheet and show you, but can you see that when we start shifting things, so if we've got our basic Z and then are we listening, Tom? Can you not? But can you look at the board and what we're talking about, right? When we are shifting this now, when we have actual numbers, so to speak, so we've got our original, a complex number, but take away 2 plus I. So this is minus 2, that's the real part. What's it done in relation to the real axis? Minus 2, it has actually shifted the center right by 2. Oh my goodness, translation. With the plus I, instead of going, instead of going bracket, it's gone down. Did I stuff that one up? 2 minus 1. Yes. Okay, because we pull out that minus. So that's how we get our translations going around the place. But of course, I could ask you to prove it. And that's the proof on the left-hand side. So we will come and do some more work on that via a worksheet, but they just didn't give you an awful lot in the textbook. But it's sort of hopefully giving you an idea of how you end up finding the equation of, or the equation of the locus of what it looks like. Does that make sense? And then we've also got the ones like this, which go, so part C, that's when we're saying the distance between this equals the distance between that and the same complex number minus another real part. So if you look, it ends up being the perpendicular bisector. And the maths that goes with it, again, it's not difficult, but it's just a lot of squaring and gathering like terms and simplifying and blah, 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 blah. So it can be a little bit annoying, but part C is crazy, because what you would need to do is actually put one of these on the other side and then square the whole thing. So you've got 8 times root whatever, root the modulus of, and so on. It's just too much. So I just thought we'd leave that one. Okay, so have a think about those. I do want to now have a think over the weekend with those, but I do want to move it along because suddenly I look at the time and bingo, bango, bob, we're gone. What you're going to be doing is quite nice. Okay, not as much. You've probably done the highest algebra at the moment. Now it becomes pleasant. So those of you with your note pages. Hey, Will. We're going to look at a thing called polar form. And you will see this a lot now, cis theta. So if we just scoot on a little bit, you can see that complex numbers are going to be written as cis something. That's polar form. One of your questions will be, can you transfer from Cartesian form to polar form, from polar form to Cartesian form? You can use the calculator. We can also use de Moivre's theorem. Now, this is also helpful. Do we know why it's cos theta plus I sine theta? Why can any complex number be written as, so polar form, so we've got cis theta equals cos theta plus I sine theta. Right, so go back to our good old plane here. And imagine that we have a complex number. Okay, so if we consider 1 plus I root 3, what does that look like on our Argand plane? Right, so we're going to go across here. 1, is root 3 bigger than? Yes, root 3 is bigger than. Make it somewhat to scale. So as a vector, that's what we look at. Do we agree? So basically, this is 1, this is root 3, and this is 2. Agreed? You don't have to write all this down. I'd rather you just listen at the moment. So why are we saying that a complex number can be written in this form? Because this is basically your real bit. Agreed? And if you look back at our triangle here, what is cos theta? Cos theta is adjacent over hypotenuse. So if I look at what is adjacent over hypotenuse, we've got 1 over root 2, 1 over 2, 1 over 2, 1 over 2. Yes? 1 over 2, and this is your imaginary bit. And of course we've got sine. So sine is opposite over adjacent, which is then root 3 on 2. But you're going, well, these don't match. Opposite, I said opposite over hypotenuse, sorry. I wrote it. I'm saying something different. I'm having a struggle town at the moment. Apologies. Hello, Georgina and Tyson. Sorry about that. Recording. No, you're not taking notes. You're just seeing how they're connected. But why are these not the same? This is 1, this is I, this is root 3. Not I, root 3 on 2. Why? 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 Yeah. So if you times that by the length, what's 2 times 1? Geez. What's 2 times a half? 1. What's 2 times root 3 on 2? I root 3, right? So this is our polar form bit. But it's coming from, this bit here is your adjacent, this bit here is your opposite, and that's how they're linked with our cosine and sine. Sort of stuff that up a little bit, but anyway. Yeah. Okay, so how do we write this in? We have to find our theta. How do we get our theta there? Yep, you can get the inverse. We should have known that one already, but let's go with sine. We could have done tan, but let's go with sine of what equals root 3 on 2. These are ones that we should know. I gave you the hard one. Pi on 3. So does it come as any surprise that my polar form for this would be 2 cis pi on 3? Because what is cos of pi on 3? 1/2. What is sine of pi on 3? Root 3 on 2. When I times it by this, bingo, bango, bob, we will get 1 plus I root 3. Got there in the end, but made a bit of a meal of that. I was going to say, you're better off not writing any of that rubbish down and just being clear with what they had in your textbook. But I was just trying to explain, but maybe it got a little bit funky there. One of the properties that is also handy to know is the conjugate. Right, looking at this little bit here. Why do we then say, yeah, that marries with cos theta take I sine theta? I need more room. So again, don't need to write. I'm saving this and you can go back and ignore it or whatever. But we have got, here is a complex number. Its conjugate, we now know, is reflected in the real axis. Agreed? So if this is theta, what is this angle here? Negative theta. So when we pop it in, we've got cis of negative theta. That becomes cos of negative theta plus I sine of negative theta. Why isn't it minus cos theta? Because that's a property, that's right. Cos of negative theta is actually just cos theta because it's the mirror image in the y-axis. It's an even function. And then this is going to be minus because sine of minus theta equals minus sine theta. So just a cute little thing. It comes up every now and again where you have to look at that with the conjugate. All right. Nice things. Polar form, your angle always has to be between pi and minus pi. So notice this one here, you cannot go around. I'm just going to draw my book now. You cannot go around and say that that would be 7 pi on 4. No good. It has to be between pi and minus pi. So just little things to go on, but quite nice, quite nice. Do we understand why this is polar form of 2 cis pi on 2? We get the magnitude here, 2, which comes from that length, and I is straight up, so what's my angle? Pi on 2. Minus 3, that's just pi. Technically you could say minus pi, but why would you go positive? And again, with this one, how do we get our angle? Use a bit of trigonometry and away we go. Will your calculator give this to you? Yes, it will, like we did the other day. All right, so, oh yeah, Georgina was here for that. So you would go, I was right on it. Where would we go? Option, complex, more, put your complex number in, and then press that. All right, so it's just getting used to. So it's going to go through and ask you, can you put it in polar form? So once again, you're practicing by hand, then using it down here. It's asking you to go hard and go technology. But yeah, it's quite nice. And then they're looking at your properties of cis theta and proving them, which I think you can probably do. So you don't need me much for this stuff, but I'll put a video up if you get stuck. And going through so you can look at it just in case. But can I ask for homework? Can you try and finish off anything you didn't do from the exercise we just did then, but not the last part C? 4C1, yes. And am I pushing my luck to ask for 4C2? I would really like it. It's just making use of these properties. Right? When you're timesing, where have we seen this before? when you're timesing by the same base? Add the powers, dividing by the same, no, they don't like it. Okay, but look, very, very nice. You got cis times cis, it means you can just add. You can use your calculator to add that up. You just have to check what's gone on, simplify, simplify. Just make sure, if this was a 15 pi on 10, you would have to change that because that's more than pi. It has to be between pi and minus pi.